So the easy. This was the last result that I told you in my last lecture. So we have yellow bundle. Its fibers are Newtonian pieces. And E is the corresponding Newtonian time of units P, which is an element of P, the element of orbital space. So I'm just going to talk about the connection induced on the fiber, okay? So it is the connection on the yellowing bundle will be its lift in the mathematical sense. So in Newtonian free space, you are using test particles for constructing the coordinate axis of our inertial frame. Okay. So forget about the local gravitational field of the Earth. So you have a particle, you just give an impulse, and it goes downward or upward according to the initial impulse. And this will be the z-axis or x3 axis of our inertial system. And the similar situation will be done for the other independent axis. The unit vectors of these axes will be orthogonal with respect to the Euclidean metric tensor field. Okay? So this gives on each fiber and every fiber a connection. Okay. So we have that axis, which we call x3, x axis, which we call x1. So these are determined by the freely-flowing particles with some specific particular initial velocities in the corresponding directions, okay? So, we have unit vector fields here. Generally, you call, undergraduate lessons, these are x hat, y hat, z hat. But now we call it E1, or I will. So these are algebraic vectors, and as Özgür Hoca told us in his previous lectures, there corresponds analytical vectors that are derivatives on the functions living on the manifold that you are considering. Okay. So let's say this will correspond to the over x1. This is the over dx. Okay. So, since these are the trajectories of our free-flowing particles, they are moving on with uniform Newtonian velocities, okay? So the condition will be like this. So the indices are running from 1 to 3. Anlaşılıyor mu? Yeşil yaz. Sorry. Netliğini ayarlayabiliriz.
Netlik pozisyonda bazen değişiyor hocam. Buradan bilmiyorum şu anda nasıl ayarlanıyor.
Evet yani öyle oldu. Bu sefer şeyi kullanmayacağız.
Projeksiyon.
Geri kalan günlerde sınıfta mı olacak öyle mi?
Bana mı söylüyorsunuz?
Sabah sanki geri kalan günlerde farklı olacağına dair bir şey.
Yok. Burası genelde burada yapılacak.
Hocam az önce yakınlaştırdığınızda daha iyiydi yani.
Hocam öyle kalsın, buradan bunu yapalım.
Netliği bozuyor değil mi? Bence öyle değil. Peki şu ufak tatlı için bence. Böyle güzel.
Şu anda Zoom'dan da biraz önce daha iyiydi diye şeyler var. Şimdi onlara da daha iyi geliyor.
Şimdi daha mı iyi?
Daha iyi.
Peki, öyle devam etmeye çalışayım. Tamam. Ben bana dikkat etmeye çalışayım. Bu kadar bölünürsen hiçbir şey anlatamam. Okay. So, this condition means that these vector fields are parallel. What do we mean by this? So let's make a quick view on the theory of connections on the manifold, okay? For a general manifold, then, this is the tangent bundle effect, okay? Özgür just started to define. So it was the disjoint union of the tangent spaces at each point of family. So this gamma represents a smooth section of this. So what does that mean? When you take an element of this, you put at every point a tangent vector on the manifold. So this is a vector field. Okay? So if X is an element of this structure, it is a vector field. Okay? If you put a star on it, so it's the dual cotangent space, namely the cotangent space at the point M. So you take this disjoint union operation and construct the cotangent bundle of the manifold. Okay? This means that if you take an element of this object, you put at every point a cotangent vector, a dual vector, or a covector, or a covariant vector. Okay? So this is a one-form field. In this case, this coincides coincides one-forms. Okay. This is the one-form bundle. One-forms are equal to dual vectors or covectors. A connection is a mapping from smooth sections of tangent bundle Cartesian product of itself to the itself. So if F and G are functions over N, it is identically this function. Okay. So F takes a point of M and maps it to R, and this is done smoothly. Okay. And if X and Y are vector fields, then connection satisfies this property. And also put Z here, okay? Another vector field. Secondly, it's take X and Y from this set. This definition. Okay. This is only related with directions. It's not related with magnitudes, okay? As in the axiomatic approach to vector spaces in linear algebra, you may recall it. Okay? I'm writing here. So when you can concentrate on a patch on the manifold, that's an open set for its topology and also for its differentiable structure, meaning it's an element of the atlas or the domain of the chart belonging to that atlas. Okay. Locally, I can say that this it is an open set of the manifolds. Okay, and this domain is this open set is the domain of the chart. This element of the maximum. Then this is the modules of vector fields over U. Okay, this is a module. You can always locally find a basis, local basis for this module. But if you put M here, generally you cannot do this. So if you want to remember the correspondence between vector spaces and modules, I will also say that this set of smooth functions on a manifold is a ring, okay, algebraically. So this is a ring, this is a module. But if you work locally, then its basis Is would be this. And if you put a star here, spaces will be these one forms. This is again the cartoon. There. Okay. But this is let's put Greg indices because we are using these indices when we are dealing with Lorentzian manifolds, as in the theory of general relativity, Einstein's general relativity. Okay. So this is the natural dual action, and this is the chronicle action. But you can also, if you have a metric G on M, it's Lorentzian. Then you can also prefer to use G orthonormal frames, which I labeled Latin indices on the below of the alphabet. These are different, okay? This is the natural basis, natural frame. These are G orthonormal frames. I will say, I will write what I'm trying to tell. And this is G orthonormal. These are free, co-free. So when you apply the corresponding group in 4 dimensions, this is Lorentz group, you can change this frames to another frame, that is G orthonormal. If G is the Minkowski metric in special relativity, or a Lorentzian metric in general relativity table. Einstein's gravitation. So this is here the dual action of a coframe one form on a frame field. So these mu's were labeled space-time indices. These are Lorentz indices. They also, in 4-dimensional case, if M is a Lorentzian manifold in 4 dimensions, these will E0, 1, 2, 3, and also A, B is running from 0 to 3. But categorically, they are very different. Okay? Because G orthonormal structures reflect very naively the metric structure residing on the manifold. The manifold is endowed with a global metric tensor field. That's a global field. But we always work locally and try to gain some global results. So this is the main point of differential topology when you use it for extracting physical information. Now, when M is flat, let's say Rn, because I'm going to work in R3, okay? Hamiltonian spaces, and it has an absolute parallelism. Its basis vectors, vector fields are all parallel, and it is valid at every point on the manifold. Okay. So this is where the connection forms came into play. Okay. So J C is a dummy index. There is a summation over it. A and B are covariant indices, and they are free indices. So which we denote by, this is my notation, which I use. A, there's a gap here. B, C, B and C have no gap, although C is at the top, B is at the bottom. These are the connection coefficients. Okay, these are the connection coefficients. But in modern differential geometry, specifically in Einstein's theory of general relativity, I'm not going to define them, but there's a torsion operator, and this operator produces the other torsion quantities, torsion coupon, torsion angle, or its contracted versions, etc. Okay, and there's also a curvature operator, and it is also defined with respect to the connection that you are using. Okay, in modern differential geometry, if the torsion is vanishing and the parallelism structure respects the magnitudes, this is called metric compatibility, then there is only one connection satisfying these conditions. That's called the Levi-Civita connection. Okay, that's the connection that we are always using in classical theories of gravitation that are not including torsion or metrics. Okay, so yeah, Y is a vector field and is parallel. This is a definition. If del x y is 0 for every vector field on M. This is called a parallel vector. Okay. But yeah, which one? No, it's a definition. Y is a vector field on the manifold, and it is said to be parallel if and only if maybe you can say it's the definition. This is due to Paul Halmos, great mathematician. Its covariant derivative with respect to any vector field is 0. Okay. So this is also called covariantly constant over M, the whole manifold. Okay. So I talked about the module structure of local vector fields, and you cannot generalize or extend to the whole manifold for constructing the basis for vector fields, and also for one-on-one fields or corrective fields. Okay. Specifically, if you have a curve, let's say the curve, the middle line. So curve is a mapping, okay, from some sub-interval. It may be open or closed with respect to the usual topology on the real line, okay. If it is a closed interval, then you fix the points. Okay. If it is not closed, it's an open interval, you can extend it as far as you can. So it will not be a compact curve, okay? It will be infinite. Okay. So there is a vector field which we don't know. Gravitation is this is our manifold. So you have a vector field. At least on a local domain containing some part of this curve, okay? This is the image of our curve. So it also has support on this curve. This is the y vector field. So you use a parameter, that's t. So this point is c of t. This will be, later on I will define what I mean by this. G of t, the tangent vector at point ct. So this is our y ct. Now, if this condition is satisfied, then stop. Then y is set to be parallel or covariantly constant along C. Note that C is a mapping. It is the curve. Its images what you see with this field. So in our Galilean bundle construction, so we pass to the fiber. It is isomorphic to the three-dimensional Cartesian space endowed with an Euclidean metric, which we call three-dimensional Euclidean space. Okay. So there is a natural connection with parallel vector field basis. Okay. This is 0. So I can write this as del according to our J, I, J. This is 0. Okay.
it's only possible if the space is flat, right?
No,
If-
in flat spaces, it's always like this. But there are also other manifolds, especially the parallelizable spheres. So the parallelizable sphere,
If the metric is not in closely metric, right?
yeah,
We can still have this condition.
you can find manifolds
Manifolds.
and all these different metric tensor fields satisfying these conditions. But they are really hard to find. The zero sphere, one sphere, three sphere, and seven sphere are parallelizable. Others are not. And these are related to the non-division algebras on real numbers, complex numbers, quaternionic numbers, and octonionic numbers. Our nature is like this. I don't know why. Magic, pure magic. Okay. See the top. So, so our particle is moving in an Newtonian space along a trajectory parameterized by the universal time parameter Newtonian time. Okay? In classical mechanics. So, for simplicity, I will give an example for the situation and taking the fiber to two-dimensional Euclidean space. And the three-dimensional case will be your homework, the hard draw. So let's start. So you have R2. So it has a three-dimensional Galilean bundle. You can use a coordinate system, which is the adapted one, the Cartesian one. You denote by X and Y. Okay, you can also use the triangle coordinate system. This is the polar coordinates defined on the polar chart. So, it's the domain of the charts. Okay. So we know that these are our coordinate systems, different coordinate systems with non-empty intersection. Okay, this coordinate system, the polar chart, has a coordinate similar at the 0 point, corresponding to the radial coordinate. Okay? So it's not covering all of R2. There's a point, the origin is missing in this description. We should know that, okay? So we can find global basis for this manifold. These are, let's say, the F spans d over dx. This is d over dx1, or the abbreviated with this partial d1. D over d1. So the same thing is valid for the vector fields induced by polar chart. Okay? note that these are the ones that we assumed at the beginning. X. X. Y. All that. This is the thing that I mentioned you at the beginning. So these are the conditions. Okay, but these do not satisfy this condition. Okay, let's try to compute this. For example, we have to calculate these things. Calculate this. Well, but before passing to that operation, so we know that this will be this will include those things. This will be this will give these two connection coefficient functions. And for example, this will give the other two, theta r and theta r theta. And similarly for the below calculations. So these are your homeworks, will be your homeworks. I will calculate this thing.
Ben de programı 3.30'da bitirmeyi o yüzden koymuşuz yani. Altıya
Okay, that's so we should write V over, this is an analytic vector. Remember that it was algebraically R hat. Analytically V over dr, it's a derivative on the ring of smooth functions on R2, okay? So we can write this as it's terrible. This was R cosine theta and R and theta are independent. So here comes cosine theta, which is x over R. So this is since theta and y over R. So we have found the vector field dr as x over R dx plus y over R dy. And similarly for your theta, this is d theta x. D over d theta as a vector field acting on a function. Specifically, this is the local charge coordinate function. So I'm not going to write them here. I will just copy it. It is not a homework, but please try to calculate these things by yourself, as Özgür has mentioned before. Okay. So this is minus y dx plus x dy. So this is a Killing vector field generating the rotations on the path plane. This corresponds to the radial translation. So you should use many derivatives for generating the flows of the corresponding motions in the translation or rotation. Özgür Hoca is going to talk about the derivatives later on. Is it true? Okay, so I'm not responsible for it. Okay. So let's calculate this one. We are this is so remember the rules for defining the connection. Okay, I will use them here. Right. Uh, X plus yellow dot dy dr that is x. Maybe you can write this one or x now del x del one plus y now del y dr. Okay, this is Oh, I'm doing something wrong. No. Sorry for this. I will put dr here and expand the other dr. Okay. Sorry for that. Oops. So keep it here. X plus year over dy. So this is dr x over r dx and dr dx plus dr acting on the function dy plus y over r not dr dy. Okay, note that there's F linearity in the below argument. So let's say this is x over r del x del y, which is 0 because they are parallel. And y over r covariant for lambda y with respect to so one. Okay, this is also 0. So this is 0. And this is also 0. And there's an x over here and plus. Okay. This is also 0. You know why? Because this is cosine theta. This is independent of the r direction. This is 0. And this is also 0 because this is sinus theta. So what we have found is this. Çünkü daha çok yavaş gidiyor.
Evet. Yani normalde 40 geçiyor bitti normalde ama siz
Okay.
uzatmaları yani.
So this was and we found that this is 0 from linear algebra. It means that this is 0. And this is also 0. So, you know, in your homework, you should find there are 8 of them. But 3 of them are from 0. Okay. Homework. I should put a prime here, okay, prime. Because the unprimed ones were zero, all of them were zero, because of the global parallelity of the local bases corresponding to Cartesian coordinates adapted to dimension of medium. Please, okay. Please put primes before the ones that I have written. There are three connection coefficient functions that are different from zero in this portion. So I want to continue a little bit. How many minutes? 15. Yani burada nasıl hesap yapılacağıyla ilgili bilgi vermeye çalışıyorum. O yüzden yani söylediğim şeyi bitirmem lazım. Eğer dinlemeyi istemeyen varsa çıkabilir, ben devam edeyim. Okay, thank you. So, I'd like to test to ensure, okay? I want to define the acceleration of a curve. So, acceleration of a curve is something. Not usually.
Dağınıza
So you have a curve. It is defined in the closed interval with boundary points 0 and 1, 2 are 2. Okay. You parameterize it with some parameter. So this is okay. But you have two coordinate systems. And this is x and y, and also r and theta. The unprimed coordinate functions. And yani radyatör müyüm, hoca mıyım anlamıyorum. Peki. Biri beddua ediyor bana çok işte. Yani burada iyi bir şeyler yapmaya çalışıyoruz. Eklesin lütfen kimse. Okay. Bunlar okay. So this can be written this is the composition of matrix of it, okay, as everybody knows. One. So in the Cartesian chart. Okay. Here we have okay, I'm going to use this one. Bilgi için örnekler görülebilir. physics. So in polar chart we have the composition of these maps acting on the parameter and as it may. Sure. So this is, I have to mention the embedding of things into another thing. Okay, so we have a curve and a closed interval. It's a curve in one dimension on the real line, and it has fixed endpoints. They are fixed, okay. But this is a compact thing, and you map it into R2, two-dimensional Euclidean manifold, real plane. Okay, so you can change its shape and you can do everything, but in a smooth manner because it's a smooth curve. Also, everybody knows that in one dimension there is no notion of curvature. Okay, this curvature is extrinsic curvature. Also in the circle that S1 so has extrinsic curvature. It's not intrinsic because you cannot define curvature tensor on a one-dimensional manifold. Okay. So this is in. So I am again making modern differential geometry in a coordinate independent manner. So this is the pullback of the x coordinate to the real line. Okay, this is defined as I denote this by capital X. So this is capital Y. This is capital R. This is capital theta. So those become X of t, Y of t. These are the Cartesian components of a point moving in two dimensions. Okay, so this is R t, theta of t. So these are the positions in one chart, and it's represented in another chart. So these are, as Dr. Özgür taught you previously. So you have two charts, they have an intersection. You take a point at that intersection, and there's only one point, nothing is moving. So you have a diffeomorphism, but it is not an active diffeomorphism, it's a passive diffeomorphism, okay? You just view at the same thing from two different perspectives. From one chart and the other chart, they have an intersection. Birazdan soyunma. Okay, so the acceleration of the curve is a vector field at some point of that curve. It is like parameterized with this t. In our classical mechanical problems, we know that it is the universal Newtonian time. Okay, this is the tangent is c dot t, and this is a c. This is the acceleration. Okay. This is the exploration vector, and this is defined by equation, sure. Okay. If it's zero, we call this curve an autoparallel of the connection number. Okay. If this condition is satisfied, then C is an autoparallel yes, an autoparallel curve of nabla in okay, this is our definition. Note that previously I put here a vector field. It was y, and told you that if this is zero, y is parallel along C. But now I'm putting a particular vector field belonging to the curve itself. It is the tangent vector field of the curve. And if it is covariant constant along itself, then it is called an autoparallel. Okay? Up to now, I didn't use the metric structure of two-dimensional Euclidean space. Okay, or in polar chart, this is VR. These are all Cartan derivatives, not ordinary differentials. Okay, this is called autoparallelity condition, which means that if you are representing your classical point particle by a geometrical point in its geometry, so this means that it's moving freely or flowing freely. Okay. So everybody wants to tell this curve the name geodesic, but it is not a geodesic. It's an autoparallel curve. If this connection does not change this means that the directions are not changed during the transport. So this is parallel transported along itself. That's the reason where the name came from, okay? Autoparallel. But when you are parallelly propagating a vector field along a curve, its direction is not changing, then it's covariant constant. If this is its tangent vector field, then if it's covariant constant, the curve is called an autoparallel. But if you have a metric on that structure, then you can make measurements with ideal rods and clocks. Okay? And if this is the length of the vector, now you have failed to define a length because you have a metric. If you don't have a metric, you can't talk about the length or angles of vectors or vector fields. That's very important. And when you are parallel transporting something, a vector, let's say, if its magnitude is not changing, this means that this condition is satisfied. This is the non-metricity tensor, and it's zero. Okay. Then this is called, this is called the geodesic equation. Okay, autoparallel equation really describes what we are looking for. But when you are dealing with Einstein's theory of general relativity, that's a classical theory for gravitational field. Let's say. This is the main object there, and it has dynamics. It resides in the equations of Einstein. You also you also have this condition, and also the torsion tensor of the connection there, and also here is 0. So this is Levi-Civita connection. And when you have Levi-Civita connection, its connection coefficient functions are termed as Christoffel functions. So I want to calculate this condition, but you have to write what C dot T is. This is the tangent vector of the curve C at the point C of T. Okay. I want to calculate this. I want to show you what this is. You know. So this tangent vector of the curve C at the point CT is defined like this. This is a push forward map in modern differential geometry. So which you map is the local basis element of the real line. So you have the real line here. So you have an interval, it's closed. Example, this is T and it is oriented. So this is, let's call it T0. So this is d over dt at T0. It's an element of the tangent space of the real line at the point T0. Okay. Okay. So formally, now you have x here and dx plus push forward of the basis element or the basis element of the global module structure of the real line, and acting on the coordinate function y, y, and d over y. So this is defined by d over dt, pullback of x to the real line. This is x composed by the curve, so which we call the x over the t. This is x dot. Okay, so the tangent vector at the point is x dot dx plus y dot dy. So similar things in the polar chart also apply. R dot dr plus. Okay. So we want to calculate the acceleration of the curve. So I will use this one because it's easy. The other part that you can construct and calculate by yourself, okay? This is E dot T. X dot X. Y dot Y. This is T dot T. X dot. Because of this calculation, you can show that this is X double dot dx plus T dot T acting on Y dot here d o dy. This is also Y double dot. Let me finish by writing this thing in the polar basis and then finish my lecture. Just a minute. This will be what you will find when you calculate this acceleration in polar frame. Okay, so this is a thing that you all know. When you calculate the acceleration of a point particle moving in 2 dimensions in polar coordinates, this is what you will find for the orthogonal components of the acceleration with respect to g, Euclidean metric g. Okay. So this is another homework. Homework 4. All right. Radial components. transfers. Transfers. Let's stop here. Are there any questions? So our next goal in the other lecture will be to give the Newtonian postulates for classical mechanics by using the standard connection on the Newtonian space. Okay, this will be our goal. Are there any questions?
What's the last homework? I didn't get. What's the last homework? I didn't get what
Yeah,
you're
okay.
gonna do.
So your last homework is calculating the expression in the polar frame. The acceleration components with respect to the polar frame. You will use d over dr and d over d theta for the basis vector fields of the basis. Okay, are there any questions? Other questions? Teşekkür ederim.